as we go. So just to emphasize the first bit of housekeeping, which is that this will be recorded and is then going to be available on our YouTube channel at a later date. So if you don't want your face to appear, then just keep your video off. And whilst we're talking about videos being off, during the session that we're going to have later, and we're going to hear from Philip Martin and Simon Portman from Marks and Clark. Can we please switch our videos off, because it slightly improves the quality of the video at a later date. Anyway, so welcome to the November edition of the Clinical AI Interest Group. Welcome to anyone who has been before, but particularly warm welcome to anyone for whom it's the first time joining us this evening. We've got a really exciting program lined up. We've talked a lot about regulation over the last couple of months, and therefore it seems very fitting that we might be moving into the more legal areas of algorithms, and indeed patenting of algorithms. And so really excited to hear what Phil and Simon have got to say to us later. Just a couple of introductions. So my name is Nick Fuggle. I'm an NIHR academic clinical lecturer. Oh, can anyone hear? Yeah, great. Academic clinical lecturer in rheumatology, based down at the University of Southampton. Yeah, it's a great pleasure to be here this evening. We've had lots and lots of involvement in response to our call for people to offer up different elements of our session. So that's the headlines or the news session, the 3-minute introduction or about me session, primer talks, but also thematic sessions, which are the bigger pieces, for example, that Simon and Phil are going to be giving us today. In fact, so much so that I felt a bit like Father Christmas coming to my inbox the next morning, and I could barely get through the door for the pile of offers that people have made. So thank you so much for those, and we're going through them and getting back to people and working on the programme for the next few months. So thank you for those kind offers. Before December, one of the things we really want to do is to run a census. So this is all about making sure that everyone is counted, but also establishing the geography of our group so that we can then engage with some of the other programs within the Turing and some of the other projects that are available. And we're getting quite a lot of offers from people. So we just want to know what kind of clinical expertise we have, what kind of data science expertise we have, so that we can create something called supra groups. We don't want these to be subgroups, because that sounds like they're underneath the interest group. These are people with supra degrees of interest in these particular areas. So we'll be developing those and aiming to launch those in the new year. So make sure that you fill out the census when it comes through. But with that, we're going to move on to our headlines section. So this is where we talk about news or developments within the field of clinical AI. And I'm very pleased to say that today we're actually joined live by Dr. Alex Deng, who is a clinical geneticist from Guy's and St Thomas's Hospital. Now, I've heard tell of clinical AI fellowships. They have sprung up on social media platforms, LinkedIn, Twitter, etc. But I'm sure a lot of the rest of the membership are really keen to hear more about them. So Alex, would you mind telling us a little bit more about the clinical AI fellowships?
Yes, of course. Just a mic check first. Everyone happy and can see and hear me? Fantastic. So by trade, as you say, I'm a clinical geneticist coming into my final year of training, but by night, I work in the clinical scientific computing department at Guy's and St Thomas's, where I was the first clinical AI fellow, having done a sort of internship there. It's very difficult for clinicians to get a chunk of time out of their training to upskill themselves and become a person who's able to deliver transformational clinical AI in their departments. So the point of this fellowship fellowship in clinical artificial intelligence is to give clinicians in training, so registrars, ST3 level and above, if you're familiar with the ranking system. But if you're not, it's senior clinicians who are on the cusp of becoming consultants, of becoming the sort of people who are going to make service level decisions and bring those benefits in clinical AI back to their specialties. We started our first cohort this year, and we're in London and Kent, Surrey, Sussex regions of Health Education England. Cohort 2 is just about to recruit, and in cohort 2, we're branching out to more regions: East and West Midlands, Thames Valley, which is Oxford and surrounding areas, East of England, which is Cambridge and the surrounding areas, and Southwest, Bristol and the surrounding areas. We're looking to make headway in new areas in future, but I think that's ambitious enough for now. Let me tell you about what actually happens on this program. Once we've selected our cohort of fellows, there's 2 elements to it. And we're trying to target the AI life cycle. I should have brought a diagram, but I'm sure you've all seen the NHSX diagram of, business and use case, building, validation, monitoring, evaluation, etc., etc. The core unique selling point of this program, which is 2 days a week for a year for these fellows, is that they are attached to a clinical AI project in an NHS trust, and their work is relevant to clinical workflows. So that's really the jewel in the crown of what this program is that they're getting, real world, on the ground experience under the mentorship of a world or national expert in clinical AI to upskill them and get the skills that they wouldn't be able to learn. Even if they did a master's or a PhD in machine learning, these are the skills that are right at the interface between being a clinician and the knowledge of what a data scientist knows about AI and how to apply it and make it interoperable, and how to comply with regulations and standards, all those juicy things that the textbooks haven't been written for yet. So I guess my ask for this meeting is, if you think you've got a team involved in clinical AI and you have projects available in clinical workflows, please get in touch with us if you think you're relevant host organizations. As I said, these fellowships are fully funded by Health Education England already. So the win for you is that you get a senior clinician who's well experienced in digital technologies and able to do quality improvement and validation projects on AI. The win for the applicant is that they get to spend a year specializing in this, and HEE gets to develop their curriculum and upskill their workforce. I put the email address of the AI for Value-Based Healthcare umbrella org that we work under, and a link to our first cohort. You can see our beautiful fellows on that landing page. I'm very happy to answer any questions that you might have.
That sounds amazing, Alex. It's so great to hear that deployment and translation is right at the very heart of these fellowships. If I was running a healthcare startup working in clinical AI, would I be eligible to be one of the organizations that's involved, or is it just NHS trusts?
This is something that we're working on for our sustainability in terms of how do we fund this, especially as Health Education England is being absorbed into NHS England. Industry-based projects do have the potential for this if they are involved in clinical workflows, and we can see a situation where industry sponsors specific places, a reserved number of places to work on their product for instance, in a validation protocol or trial at a particular trust. We'd have to work out the details, but that is something that we'd want to work with.
Brilliant. Oh, well, they sound so exciting. We probably do need to move on just for the moment, but thank you so much for putting your contact details. Did you say they were in the chat?
Yes, I have put them in. Could I quickly cover Emily Clark's questions?
Yeah.
The funding does not cover the clinical days. They remain, so the clinician remains in post for 0.6 of their time, or if they're taking less than full-time training, an even lower percentage of their time. That's still covered by their training program, and for that reason they need a national training number in order to apply to this program, so that they do have funding for the rest of their job. Does it extend CCT? Yes, the clinician would have to apply for less than full-time training in order to reduce their training counted towards completion of training, certificate of completion of training by a commensurate amount. However, it's not as disruptive as doing a master's or a PhD, which is that opportunity cost is massive. So we're trying to reduce the friction and being able to become a clinician who's got this expertise. And the last question, are there less than full-time options? Yes, you have to take less than full-time training in order to become one of these trainees, these fellows. If you have specific questions, Emily, please do address them to the email address. It sounds like you might be, or someone who might be considering this.
So there certainly sounds as if there's some interest out there. Brilliant, Alex. Thank you so much for joining us and telling us all about those clinical AI fellowships. And do get in touch via the address in the link. Is Alicia out there? Alicia Davies.
Hello, Chris.
Hello,
Nick. Yeah.
hello,
I'm
Alicia. Lovely to see you. Welcome. For anyone who doesn't know, Alicia is one of the co-organisers of the Clinical AI Interest Group, and joins us from Wales. Is it Wales this evening? Or
yes,
is
it... I was bombing it. Well, not bombing it. I was driving at the regulated speed limit in horrendous rain down the M4. I've just been in Port Talbot all day, so today's been a bit manic. But yeah, I'm here. I'm glad I made it, and I'm linking into the next item, aren't I, Nick? We've got 3 minutes. Thank you to everybody who's volunteered in the About Me slot. We've had a fantastic response to that. So we hope to, get through everybody. And also I'd encourage you not just to link up in this 1 hour that we can capture your attention for. Like, it's a clinical AI network, and there's an open email where actually you can reach out to members. So please do that. It'd be lovely to see all those other links building up.
Yes. Okay. So we've been through our headlines. We've had a 3 minutes about me session. So now we lead on to the thematic session for this evening, which is entitled Cutting Edge AI, Patents, Data and the Law. And we're joined by Philip Martin and Simon Portman, both of Marks & Clark, which is a legal firm. Phil started life as an undergraduate physicist. And I am actually just going to run through your bio really quickly, Phil, because I do think it is interesting. So then he left and became a teacher at Charterhouse for a year, and then thought he'd had enough of that. So then went and did a PhD at Cranfield, and during his time at Cranfield was shortlisted to be the UK's first astronaut, which I think that's a first for the Clinical AI Interest Group. Anyway, he since then moved on to his current life as a patent lawyer, and has worked with various different organizations and companies, including DeepMind, and has worked with them on the AlphaFold project. And we're also joined by Simon Portman, who is of counsel at Marks & Clark, specialising in contract law for technology companies. He started his undergraduate life at Oxford, but actually currently is a guest lecturer for Cambridge, so I'll have to ask him who he supports during the boat race. But he's also written 2 textbooks, including one that's entitled Commercial Issues for Life Science Companies, and so therefore is kind of highly relevant to some things we're talking about. So I think I'm going to hand over to Phil first, and I'm going to, if we could all switch our videos off for the moment, that'd be brilliant. And I understand they'll kindly take questions at the end. So Phil, the floor is yours.
Excellent. I should now be screen sharing. Hopefully you can see a screen.
You are very clear.
Good, excellent. Okay, There's way more material here than I'm going to get through. So I'll just try to cherry pick a few things which are interesting along the way, really. So first of all, Marks and Clark, who are we? We are patent and trademark attorneys and IP solicitors. Very broadly, a patent attorney writes and prosecutes patents, and an IP solicitor writes contracts and licenses and does litigation. The images on the slide there, our founders, Dougal Clark, invented the first practical two-stroke engine, and Baron Marks of Woolwich, among other things, built funicular railways and helped to found Sevenoaks Hospital. So I'm going to talk a bit about machine learning techniques because that comes with pretty pictures, a little bit about patents, and then hand over to Simon. So this is going to focus primarily on neural networks. Probably most people know what they are, but just in case not, in the bottom left-hand corner there is an artificial neural network. You have the neurons, which are the circles, and you have lines with arrows going into them, and they are signals with weights on them, and you provide an input of some sort, which could be an image, for example, and the output might be probabilities that the image represents a cat or a dog, and then you train the neural network by determining a difference between what the output should be, for example, a picture of a cat, and what it actually is, and then you back propagate, you go back through the neural network and adjust the weights of those black lines until the output gets more like the one you want. And that's when that process is finished, you've trained your neural network to recognize a picture of a cat or a picture of a dog. The image alongside it is one idea about how backpropagation might occur in the brain with pyramidal cells. So in these other images on the slide, the boxes that you can see basically represent neural networks along the lines of the thing in the bottom left-hand corner. I'm not going to talk in detail about AlphaFold 2, but I can't help but mention it because it's such an amazing result. And incorporated in that, in making that work, is an input sequence. You process an input sequence to get an output structure, and in the middle is this block called an evoformer, which is a pun on the name, the transformer architecture. What is a transformer? It uses a mechanism called attention, and attention is responsible for a lot of the really good results that are coming out now in all sorts of fields. This is the evoformer block in more detail, and it's got in some of these blocks along the way something called self-attention. And I won't say more about it than that, I don't think, at the moment. If you need to know more about how it works, there's something called the Kendrew lecture online, which has got a great description. There's two of these lectures, one by Themis Hassabis and one by John Jumper. Very recently, Meta, Facebook, came up with their variant of this, which has got a very similar output stage, but they've got something called the language model at the front end. Again, this uses a sort of transformer type structure, which uses attention. So because of that, it's worth briefly mentioning what attention is. In a process which involves attention, you have some querying objects and some queried objects. Each of the querying objects is turned into a key, and the queried objects are turned into keys and values. And then these are vectors, basically, and you look, given a certain key, you identify, given a certain query, you look at which keys are similar, and the similarity gives you a weight, and then you do a weighted sum of the corresponding values to get the output. So that's an attention mechanism. That's at the heart of many of these really interesting results that are coming out now. This is a transformer neural network. In this, you have multi-headed attention. That is simply a set of the things in the previous slide in parallel. And this is the original sort of transformer structure. This was used for neural machine translation, NMT, and the way you use this system, you provide a sentence as the input to the encoder, and what you get out of it is a translation of the sentence into a different language. So you process the sentence, gets turned into a set of tokens, one per word, and they are encoded using this attention mechanism. And the encoding here uses what's called self-attention, where the queried objects and the querying objects are in fact the same. And then the decoder, the way this works is that you, given the input encoding, you have, you generate one word at a time on the output. So the output of this is basically, if you've got a vocabulary of 10,000 words, then it's a set of 10,000 probabilities, one per word. You pick, for example, the most likely word. That gives you the first word in your output sentence. You feed back that to the start, so it's autoregressive. And then given that word, you pick the next word. And you keep going until you get an end of sentence token. So it's an autoregressive structure. And you train it on input-output pairs. You train it to generate the output one word at a time. And you can typically train it on a very large amount of data. This example's got an encoder and a decoder. You can actually do the same thing with a decoder-only model. This is what the majority of the large language models these days use. And you simply train that on the body of free text. So, given a sentence, what's the next word? One word at a time. There are also encoder-only versions as well, which just encode an input sentence. You can feed anything into a transformer. So you can feed an image into it. You can encode patches of the image into these tokens and feed those in. And then you have an encoder and a classifier, for example. You get very good results like that. And this is a model which combines text and image inputs, and it's trained to generate images from descriptions, and it can do all these wonderful things that you wouldn't necessarily expect. So it can, for example, invert a photograph. Large language models are essentially that decoder part of the transformer. They are very large, as the name implies, so hundreds of billions of parameters and maybe a trillion training words. And these have become of great interest because they can do things that they haven't particularly been trained for. So zero-shot learning. Here's an example. So this is called prompting. The idea behind this is that you provide some input and then ask the system to generate the output one new word at a time. So the input here is an example question and an example answer, and then the actual question. And simply by having been trained to generate one word output at a time and priming it, as it were, with this as the input, it can reason and give you a reasoned natural language answer to an input problem, which is quite an amazing thing, actually, that you wouldn't expect it to be able to do. Some of these models can also reason about images. And the example on the right is a Stroop test. So there we go. At the end, how about you? I'm not affected by this difference. So, how does that come from a language model? It's almost magic, but it does nonetheless. So these large language models can do amazing things. They can also write code. So here's the input. It's a statement of a problem to be solved, and here's the output. And they can write code at a level that good humans can write. And this language model has been trained on a very large amount of code from GitHub. You could also use these things for chemistry and biology. So here's an example. You give it some text, and out comes a particular sort of drug-like molecule. And here the molecule is represented as text using the SMILES approach. And recently that's been used to also annotate millions of previously uncharacterized proteins with natural language descriptions. So as well as being used to solve problems, these large language models are being used to do all sorts of other interesting things, possibly even help your next paper. They can do, for example, summaries of papers, although you have to be a bit careful about whether or not they get it right. Another application of these is there's a company called Helix, which is basically looking at orphan diseases. And effectively what they're doing is reading many, many papers and looking for new relationships between drug and disease. So these large language models can do all sorts of really quite interesting things that they haven't necessarily been trained for. This is another category of neural network, which is getting some really interesting results. So these are graph neural networks, and molecules and other things can be represented as graphs. Exscientia is using a graphical neural network type approach to design human antibodies for virtual screening. So just to give you an idea of what's going on here, you have nodes and edges. The nodes have attributes, the edges have attributes. You have a little neural network for edge updates, a little neural network for node updates, and you apply the same neural network to update all the edges. And then after that, you apply a different neural network and you update all the nodes, and you repeat. And I'll skip over that slide. That is the same thing. Effectively, that involves message passing. Messages diffuse throughout the network, and gradually the network updates. And the sort of things you can do with that, let me see if I can give you an example. Not really time, but I'll give it a go. Okay. I'm just going to move this window across to the screen where you can see it. So is this going to work? Yes, it is. So basically, this is a graphical neural network operating on a mesh. And it just gives you an idea of the sort of realism that you can achieve, with this sort of graphical neural network structure. So you can process meshes representing cloth in a very realistic way, but you can also process graphs representing antibodies, for example. So graph neural networks. Onto another strand these days, contrastive learning. So going back 2 or 3 years, generative adversarial networks were in vogue. This picture on the right was generated by one of those. It sold at Christie's for $400,000. There is a website which allows you to generate your own, but I think it says for non-commercial use only. And what is happening here is that you have a generator neural network and a discriminator neural network. You start with noise. The generator generates an example, for example, image or something else. And the discriminator tries to discriminate between the generated synthetic example and the real example. And the discriminator learns to discriminate reals and fakes. And the generator is trained to try and fool the discriminator. And these two are trained in an iterative cycle so that the discriminator gets better at discriminating and the generator gets better at generating images that look more and more real. So you can generate realistic images. If you put a cycle consistency in that, you can turn horses into zebras. And you can use these sorts of techniques as well for other things. If you replace the generator with a classifier, the discriminator tries to predict the value of some sensitive variable. You want to make sure it can't. So if the classifier is fair, the discriminator should be sort of near random. StyleGAN, this is the generator here has got a sort of internal knob which you can use to tweak the characteristics of the output. You can use that, for example, to generate training images. So here you're taking an image of an African-American individual that is underrepresented in your database, and you're moving it along a trajectory that takes it to a location that has more disease lesions, in this case AMD. So you're enhancing your data set with this sort of approach, as opposed to putting spectacles on people. You can also use these sort of things to generate synthetic data based on real data, and with differential privacy, you can help to ensure privacy. Here's another example of contrastive learning. What you're doing here is this is self-supervised, so you don't need labels. You have a picture of a dog, a picture of an armchair. You generate what are called augmentations. So maybe you make it black and white, or you crop it. And then the idea is that representations of the dog should be similar to themselves, but different to the representations of the chair. And you make your augmentations so that they destroy non-semantic information, so that this learns a semantically useful representation of the input image. So that's contrastive learning, and there's a whole lot of variations on that as well. Here it is done slightly differently. So this is X-ray images and their text descriptions. So again, you've got a contrastive loss here. You're training it between an image and its description, or a different description. And you can then use that to train a classifier afterwards and get some good results. This is something called CLIP, which is used, I think, in DALI 2. Similar idea, you encode text, you encode images, and then in order to, for example, classify a photo of a dog, you work out what caption is closest to when you encode that text, is the encoding, which image is the encoding closest to. You can do the same sort of thing with X-rays. This is some recently published work, which is by Andrew Ng's group, among others. And essentially, you have a vision transformer, and text transformer, and you have descriptions of images, and you train it with this contrastive learning approach. And then what you do is you encode two sentences, one that says edema, one that says no edema, for example, and then you take each of those encodings and compare it to the encoding of the vision transformer, say which is most similar. This can do zero-shot learning, i.e. without further training, and it can produce expert-level results. So interesting results from that. Diffusion models are another recent development. You take an image, you gradually add noise to it, you train a neural network to denoise it. And at the moment, you can use these for generating, they're mostly used for generating really high quality images. Here's a medical use. You take an input with a brain with a tumor, for example, you effectively denoise it to get the output. And then you do a delta, which tells you where the anomaly is. As of last month, there was a project announced by this Stability AI, one of the diffusion model people. They're going to look at this instead of for images, but for text, to try to generate DNA sequences with particular regulatory properties, a sequence that will correspond to open chromatin in cell type X, or a sequence active in cell type X that contains binding sites with transcription factor Y, for example. So all sorts of promise in these models, and they're pretty good at images, so they're probably quite good at other things too. Reinforcement learning, I think I'll skip that today, except there's a rather nice use case on the Google website, which talks about how it's been used to basically select listeners who are going to most benefit from service calls when you can't bring everybody up, to improve their sort of standard of postnatal care. So that's reinforcement learning. I'll skip past that. There's a lot of basic work being done on the machine learning models for imaging tasks. This one's quite interesting, I thought. So you train a neural network, you've got a held out validation data set, you've worked out it's got good performance on that. Even when you do that, interestingly, you can change the random seed and sort of break the performance of the neural network, even though it looks to have performed well on your held out data set. So with a new camera type it hasn't seen before, the value of the random training seed can actually make quite a big difference to the performance of the neural network, even if it's validated well on held out data. So there's other things going on there. So there's lots of sort of fundamental work going on there. Why talk about patents? Obviously patents are a commercial tool, so essentially it's in the context of commercial value. The monopoly rights, basis for licensing, defensive value, cross-licensing, or there's a freedom to operate effect of patent application being published. That will stop other people getting patents. Investors often want to see patents. It shows innovation. It shows ownership of the IP. And if you're making a profit, you can get a tax reduction, tax credit on that as well. On the other hand, for AI systems, there's a lot of other barriers to entry. Software, difficult to reverse engineer. Training data might be difficult to access. If it's in a clinical field, then it may be that you need peer-reviewed publications to validate a particular model. And only that particular implementation is the one that might actually be trustworthy for other people. So that might be a barrier in itself. So they have their uses, but they're not necessarily essential. That said, other people are filing them and filing a lot of patent applications. It's fast growing in this field. I'm not going to go through all this, I don't think. In talking about patentability, in the clinical field, with a broad brush summarization, everything's going to be patentable in the States. The language model-based approaches are probably not going to work in Europe, but probably would work in the States. The key point here is if you're thinking about patenting, find a patent attorney who's got experience of drafting and prosecuting machine learning cases, because that's going to be important. You can actually make quite a big difference to whether or not an application succeeds by having seen the ways it can fail before the European Patent Office, for example, and then you can fix those problems at the start. I'll skip past that. And so on to Simon. And I'll stop sharing so that you can then share.
Okay, thanks very much. I shall now if I just so I was trying to get my slideshow started, but the button to do it is blocked out by, that's it. Okay, yeah, right, thank you, Phil. I'm going to have a quick canter through some legal issues, and because of the shortness of time, it'll be kind of high-level chat. If we haven't got time for all the questions at the end, then, as with Phil, feel free to email us or contact us on LinkedIn. Yeah, the issue that I'm going to highlight here is that, as I'm sure you're all aware, is that, the use of AI has produced a quantum leap in the ability to process and analyze data, carry out drug development and drug discovery, and carry out diagnosis in a much quicker and more accurate way. So I went to a life sciences conference in Cambridge back in the summer, and it was taking place after a 3-year hiatus because of lockdown. And the two main things on everyone's lips were, firstly, how do we replicate the open innovation and collaboration that went into vaccine development and everything else? And the other one is, what a revolutionary difference AI is making. However, there is a bit of a problem, and I'm going to illustrate this with a couple of examples of what can happen when computers make decisions for you. The first is an apocryphal story about Robert McNamara, the Secretary of State under Kennedy. In 1967, he began to realize that the Vietnam War wasn't quite going the way everyone had hoped, And he is someone who had revolutionized computer modeling and data analytics. As the youngest ever chairman of Ford Motors, he had used it a lot in the car industry, and then brought that with him when he went into politics. So he went to the CIA mainframe computer at Langley, which probably back then was an enormous bank with loads of flashing lights and whirling spools of tape. And he put all the data in about America and Vietnam, about military capability, GDP, population, resources, national character, technology. And the question he asked was, when are we going to win the Vietnam War? And the computer whirred and flashed away and eventually came back with the answer, you won it in 1965. Now, I mean, a more real-world example of this is something that I came across a couple of years ago during lockdown, when obviously supermarket door-to-door deliveries really took off. It used to be the case that if you ordered something and they couldn't produce it because it wasn't on the shelf, they would the shelf stacker would use their initiative and find a substitute for you. Now what happens, and if you want to go with that, then the algorithm will come up with a suitable substitute for what you're buying. And guy in our village, he was a builder who went into becoming a supermarket delivery driver during lockdown, said that they used to keep tabs on what was the most ridiculous and inappropriate substitute in the shopping. And the best one that happened was a woman ordered a pregnancy test kit and she received a packet of condoms. Now you can kind of see the logic there in that they are both reproductive health products, and therefore the algorithm obviously thought it was a really good idea. But from a human can just tell you it's totally inappropriate. So what these show is that, if there is either some bias or built-in flaw in the generation of the AI, or there is some flaw in the data going into it, then something less than perfect could come out the other end. And this obviously can produce significant ramifications in terms of product liability, where AI is being used in diagnosis, treatment, drug discovery, or whatever. And as it is, I hear that you've already, been talking in previous talks about the regulatory issues. You've also got the issue that, an AI product that just stores data or supplies knowledge isn't a medical device. But if you've got one that is involved in surgery or diagnostics, it could well be, even if it is one at the lower end of the categorization. In the same way that, if you have a VR product, it's basically computer game technology, but the moment you use that computer game to, say, diagnose or treat dementia or a stroke patient or mental illness, it's suddenly become a medical device. So you're getting, and that means if things go wrong, it's that much more serious. And that's one of the reasons why I mentioned there autonomous vehicles at the bottom, where there has been even more of a problem, and that is grinding to a halt at the moment, because they found that the autonomous vehicles just do not have the same ability to interpret the surrounding environment in the way a human does. So therefore, you've got a real problem here. If a person gets something wrong, or there is a mechanical failing in an object, it might be fairly easy to see what the problem is. However, where that decision-making is more removed from the end result, it can be quite hard to attribute blame if anything goes wrong. And you've therefore got to fit that problem, square that problem with the legal framework where you might under tort have a duty of care, in which case you've got to prove that the damage was reasonably foreseeable and that there is a causal link between the thing that went wrong and the loss that was caused. There might be contractual liability as well, in which case you've got to see if you can limit that in any contract. And there is also the extra avenue of negligence in terms of product liability. And so anyone seeking to attribute liability will find the link, and using these legal systems has to see where the causation lies. Is, you know, and in the context of AI clinical products, is it the fault of the data going in? Was it the fault of the software? Or was it the fault of the user? And it can be quite hard to find out who is at fault. As a result of that, there have been suggestions about how, where it might be difficult to, in a clear-cut manner, find out where the fault lies. Do you impose a levy of some sort? Subrogation means that if a patient suffers injury, then their insurance company can then automatically go after the party at fault, and then you've got to work out who the party at fault is. So this is something which the regulatory bodies in the US, the UK, and the EU are all looking at the moment. One of the things that's been concentrating in the FDA's mind is working out how you can limit any sort of bias in any product being created. I think Phil mentioned African Americans earlier, and so there have been problems already where if you generate a diagnostic tool and the data that you've informed that with is based on the predisposition to certain medical conditions of Caucasians, that doesn't always work with Black people or, say, Japanese. So you've got to ferret those out. In the UK, inevitably it's turned into quite a big talking shop, and you've got various stakeholders whose views have got to be heard, and that in terms of clinicians, manufacturers of AI products, patients, and so forth. So that's also ongoing. The EU seems to have been very concerned with the danger of any sort of clinical application of AI resulting in some sort of risk profiling modeling, which gets you into some sort of Chinese social credit system. A lot of people are worried that, however, that the EU approach is going to be so regulatory heavy that it's going to make the technology less competitive than its American and Asian competitors. And there at the bottom there, you see a suggestion where you could have some sort of levy which would pay for any loss caused, where you're not necessarily attributing blame because it's not that easy to find blame. So one thing I'm looking at as a lawyer is how this is going to work out in terms of licensing the AI, what elements you can limit and exclude under law. As you probably know, you can't exclude liability for death or personal injury caused by your negligence, and you can only limit or exclude other liability to the extent that it is reasonable to do so, and arguably, therefore, it's probably going to be unreasonable to limit your liability to the amount that someone has paid for a software license. And obviously also, insurers are going to have to look at the packages that they can supply to cover liability in this regard, rather in the same way that they are having to catch up with things like cybersecurity. Another issue to look at quickly is, you know, where you're using smart devices, sensor technology, reliant on 5G to both track patients and monitor and predict what their medical condition might be. You're going to have a privacy issue, because you're not only therefore going to be processing medical data and data that, but also data that can identify that patient in other ways, for instance, their location. And part of the problem here is, and this surprised me, is that although medical data is sensitive personal data, so there is a much higher threshold regarding protection and informed consent. Clinicians in the past have not always been the best custodians of that. I've got 3 examples that I can comment on here. Firstly, a few years ago, there was an HIV clinic where someone sent a publication to everyone on the mailing list. Unfortunately, they used CC instead of BCC, so everyone on the mailing list got to see the name and email address of everybody else who was on the mailing list of that clinic, and some of them, you know, recognised other people on it. It wasn't that great, as you can imagine. The person that made this mistake tried to compound their error by retracting the email, but they made things worse by actually sending it out all over again. I don't know what happened to that person, but they were sent on garden leave, and the manager of the clinic had to go on television and make a grovelling apology. I had a case a few years ago of a client who had developed data analytics for inputting a whole load of data on patients to assess their risk of breast cancer, so that they could then work out, you know, what lifestyle changes they should make, how often they should go for scans and so forth. This also included getting information from them on relatives, so because that obviously informed their own risk profile. Unfortunately, what the hospital my client was working with ended up doing was taking the names and addresses of these relatives, working out what their risk profiling was, and then without consent running the product on them and contacting them as well, because without asking them, because they thought it was for their own good. And I said, look, I don't really think this is okay. You need their consent. And they said, no, we're sure it's okay because we're the NHS and we have Crown immunity. And I said, well, there is no such thing. And no, you don't. And they said, we're sure it's okay. I said, I'm pretty sure it's not. I contacted the IC on a no names basis. And they said, no, this certainly is not okay. Tell us the clinic that's doing it, and we will audit them and then we will fine them. And I said, just calm down and I'll sort it out. And I did, but I was amazed they'd made a mistake like this. Final example was one that Phil mentioned to me a week or so ago, where the image set mentioned here, a woman found images of herself, which she had given to a doctor on this image set. God knows how they'd ended up there. So, you know, you have to be very, very careful about what you're doing with medical data. And the trouble is that now, with it being used in AI, with automatic processing, predictive
Simon,
models. Yep.
I'm just aware that the time.
Yeah, I'm finishing in 1 minute. So this is my last slide.
Amazing,
so,
amazing.
Yep. So you know, the idea of the clear transparency that was envisaged by GDPR, so you can know what's going to happen to your data and where it's ending up, it just doesn't look like it's going to be workable with GDPR, and it's already been left behind in the same way that copyright was left behind when we got into digitization and downloads. So I've just finished there, and where we're short of time. if there isn't time for any questions now, and there may not be, then Phil and I are both free for if you want to contact us by LinkedIn or email for any follow-up questions.
That would be brilliant. Yeah, and thank you so much for putting your email addresses and contact details up on the presentation as well.
So yeah, so feel free to reach out to us. Yeah.
That is so kind. Thank you so much, Phil, and Simon, for that tour de force of general artificial intelligence, engineering, patent law, and of course the legal elements of algorithms as well. So thank you so much for talking us through with that. And thank you everyone for joining. And our next meeting will be on the 13th of December. That's Tuesday again at 6 p.m. And there we're going to be joined by Lauren Morgan and Baptiste Vasey, who are both key in the Decide AI program, which produced some reporting guidelines for the development for the area of development to implementation gap in clinical AI. So thank you so much for joining us, and look forward to seeing you in about a month's time. All the best.